If you've ever studied linear algebra in school or college, you've probably seen numbers being written in this weird format within square braces. This is called a matrix. We are then introduced to operations like multiplication, which follows a completely different rule than what we might expect as normal, where you multiply the rows with the columns. There are stuff like finding the rank, eigenvalues, and diagonalization, which we are told just to memorize as is without ever really knowing the intuition behind them. With the help of this video, I want you to get the understanding of behind the scenes of matrices. If you've ever dreaded studying matrices in your school or college, I hope this video helps you to see them from a newer perspective. To understand matrices, we first need to see what a linear transformation is. To understand the difference between a linear and a non-linear transformation, have a look at this. Let's say we have this line. I can just rotate it however I want, and it still stays a straight line. But what if I transform it into a parabola, or a sine wave, or something totally ungodly like this? So this is non-linear. I hat and j hat. They are unit vectors, meaning they have a length of 1, and they form the basis for R2 as they are linearly independent. We've already discussed what basis and linear independence is in the previous videos. Let's take the vector v. This vector can be represented like this, or to say 2i plus 1j. Let's perform a transformation on this, and our vector lands on this new position. This new point is -2, 3. Let's also look at where the I hat and j hat lands on doing this transformation. So I hat lands on 1, 2, and j hat lands on -4, -1. So what if each and every vector present in this space also goes through the same transformation? It's like transforming the entire grid or plane. The new I hat and j hat are the new bases. So if we go 2 units in the direction of this new I hat and 1 unit in the direction of the new j hat, we arrive at 2, 1 in the new bases, but -2, 3 in the old ones, which is our transformed vector. Okay, so we did a transformation, our vectors all moved to new places, but how do we write this down mathematically? In what way can I represent this complete action? Well, I can write where my I hat and j hat lands after the transformation is done, within square braces, and that is what a matrix is. It is a representation of the action of linear transformation in the mathematical language. So say we have this matrix, where the columns represent where I hat and j hat lands. For any vector xy, we can find its new position after transformation by just simply multiplying the x by where I hat would land and y by where j hat would land. And if you haven't realized yet, this is where the intuition for the weird rule for matrix multiplication comes from. The row gets multiplied by the column. A11 times x plus A12 times y, and A21 times x plus A22 times y. There are various standard matrices for different kinds of fun transformations. For example, a linear transformation for rotation looks like this. There's something called a shear. This matrix just distorts the plane like so. Or we can have a really cool transformation like this one. Or we can have one where the plane collapses to a line? Wait, what just happened? This linear transformation was caused by the matrix where the I hat lands on 1, 2 and j hat lands on -2, -4, which are in fact linearly dependent columns. So our world of R2 was squished down to R1. Do you now see how vector independence is related to matrices? That's one of the most beautiful things in linear algebra. Matrices have countless applications such as image processing, computer vision, neural networks, solving systems of equations, and a lot more. I hope that next time you encounter a matrix, you'll see it as a tool performing a linear transformation rather than just a collection of numbers that seems to have no meaning. In the next video, we'll be looking into the different types of matrices, so stay tuned for that.